Welcome to a quiet journey through the cosmos. Tonight, we are going to explore the soft light of beginnings, the slow, patient birth of stars, and the incredible endurance of the smallest lights in our universe. It is a story that spans trillions of years, yet it begins in the most silent, hidden corners of space. We often think of the night sky as a finished map, a collection of static points of light. But the universe is a living, breathing place, constantly folding and unfolding in the dark. Before we drift too far into the stars, I want to invite you to find your most comfortable position. Take a moment to adjust your pillows. Pull your blanket up to your chin if that feels right. Let the weight of your body sink into the mattress, feeling the full support of the bed beneath you. Allow your muscles to soften, starting with your toes, then your legs, and moving all the way up to your shoulders. Let your shoulders drop away from your ears. There is nowhere else you need to be right now, and nothing else you need to do. We have all the time in the world. Our pace tonight will be slow and unhurried, like the drifting of cosmic dust through a vacuum. As you begin to settle, I'll mention very softly that if you find these stories helpful for your rest, you're always welcome to subscribe to the channel or leave a gentle comment when you wake. It helps our community grow and allows these peaceful journeys to reach others who might need them. But for now, there is no need to move. Just focus on the sound of my voice and the steady rhythm of your own breathing. Take a slow breath in and a slow breath out. Imagine the room around you beginning to dissolve. The sounds of the world outside, the distant traffic, the soft hum of the house, the ticking of a clock, all of it is fading away into a soft gray mist. We are moving upward now, through the cool night air, drifting past the clouds and rising beyond the reach of the Earth's atmosphere. The sky above is no longer blue, it is deepening into a rich, velvet black, salted with the light of 1 billion distant suns. Out here, far from the lights of Earth, the universe isn't just a dark void. It is a canvas of light and shadow, filled with mysteries that move at a speed humans can barely perceive. We are heading toward the vast, silent clouds of gas that drift between the stars. These are the places where everything begins. They are cold, they are still, and they are waiting. As we leave the familiar comfort of our solar system behind, we enter a realm that seems empty at first glance, but is actually teeming with the invisible ingredients of life. We are moving into the deep, quiet spaces between the stars. As we drift further from the familiar glow of our sun, we find ourselves in the great, silent expanse known to astronomers as the interstellar medium. To our eyes, the space between the stars might look like a perfect hollow void, a vacuum of nothingness. But in reality, it is filled with a very thin, very cold mist. This is the matter that exists between the star systems in a galaxy, a cosmic soup of gas and dust that has been drifting since the beginning of time. It is the raw material of the universe, waiting for its moment to become something more. This interstellar mist is composed almost entirely of the two simplest elements, hydrogen and helium. These atoms are the oldest travelers in the cosmos. Most of the hydrogen you might imagine drifting out here has been around since shortly after the Big Bang. moving through the darkness for billions of years. It is a strange thought, isn't it, that the very same type of atom that makes up the water in your body or the air in your lungs has its cousins out there, floating in the deepest reaches of the galaxy, untouched and serene. The most striking thing about this medium is its incredible thinness. On Earth, we are used to the density of life. The air we breathe is thick, a crowded sea of nitrogen and oxygen molecules constantly colliding with one another. Even what we call a vacuum in a laboratory on Earth is thousands of times denser than the space between the stars. To understand just how empty this space is, imagine a tiny cube, just 1 centimeter on each side, about the size of a single die from a board game. In the room where you are resting now, a cube that size contains about 30 quintillion molecules. It is a number so large it is hard to even visualize. But out here, in the vast stretches of the interstellar medium, that same cube would likely contain only 1 single atom of hydrogen. 1 single atom, drifting in its own vast kingdom of space. Take a slow, deep breath in and let it out softly. Imagine that level of stillness. Imagine the peace of having so much space around you that there is no pressure, no noise, and no hurry. In this cold, quiet realm, an atom might travel for hundreds of years before it ever brushes against another. It is a place of ultimate patience. Let your own mind mirror that patience. There is no need to rush to the next thought or the next hour. Like those lonely atoms, you are simply drifting in a calm, supportive dark. Even though this gas is spread so thin that it seems like nothing at all, the universe is so immense that these single atoms eventually add up. Across thousands of light years, this nothingness begins to have a weight of its own. It is a gentle, ghostly presence, a veil of gas that spans the distance between every star you see in the night sky. As we continue our journey, we begin to notice that this mist isn't perfectly uniform. In some places, it is a bit more crowded. For reasons that take eons to unfold, the atoms begin to find each other. Like the way breath fogs a cold window pane, the thin interstellar medium starts to gather and huddle together. We are moving now toward one of these gatherings, a place where the mist grows thicker and the temperature drops even further. We are leaving the open plains of the galaxy and entering the shadows of a cosmic nursery. As we move deeper into these shadows, the light from the rest of the galaxy begins to dim, as if someone is slowly turning down a cosmic lamp. We have arrived at a molecular cloud, what astronomers often call a stellar nursery. It is a beautiful name, isn't it? It suggests a place of protection, a cradle where something small and fragile is being nurtured into something grand. These clouds are among the coldest places in the entire universe. While the open space between stars can be chilly, here, the temperature drops to a staggering 10 to 30 degrees above absolute zero. To put that in perspective, imagine the coldest winter night you have ever experienced. A night where the air feels sharp and still. Now, imagine a cold so deep that even the air itself would freeze solid and fall like snow. In these depths, it is nearly 450 degrees below 0 Fahrenheit. This extreme cold is actually a gift. In the warmth of open space, atoms are full of energy, zipping around too fast to ever settle down or get close to one another. But here, in the heart of the nursery, the atoms slow their pace. They lose their frantic energy and begin to drift toward one another. For the first time, they are moving slowly enough to bond. Instead of lone, solitary hydrogen atoms, they pair up to form molecules of hydrogen. They huddle together, seeking a quiet stability. It is this transition from individual atoms to bonded molecules that gives these clouds their name. It is a strange paradox to consider. Even though we call these clouds dense in the context of space, they are still far emptier than anything we know on Earth. If you were to stand in the middle of a molecular cloud, you wouldn't feel like you were in a thick fog or a storm. To your eyes, it would still look like a perfect clear void. And yet, this is the raw material for every sun, every planet, and every living thing that has ever existed. It is hard to imagine how something so ghostly, so thin that it would pass through your fingers like a dream, could ever become a massive, burning star. How can a whisper of gas become a roar of fire? The secret lies in the sheer, staggering scale of these clouds. They are so incredibly large that even a tiny increase in density spread over trillions of miles creates a massive amount of matter. It is a slow gathering of resources, a quiet accumulation of potential. Inside this cold darkness, the universe is preparing to create light. But to turn this thin mist into a star, it needs a nudge. It needs a force that is patient enough to wait for millions of years. As you lie there, feeling the weight of your own body supported by your bed, imagine that same gentle pull beginning to take hold in the deep dark of the cloud. Somewhere in the center of this vast, cold nursery, the atoms are no longer just drifting aimlessly. They are starting to move with a purpose. They are responding to an invisible call, a soft, persistent tug that has existed since the beginning of time. This force is subtle, almost imperceptible at first, but it is the hand that shapes the cosmos. It is beginning to pull the molecules together, closer and closer, turning the scattered mist into the seeds of a new world. This force, as patient as the stars themselves, is gravity. In the grand hierarchy of the universe, gravity is actually considered the weakest of the fundamental forces. It is easily outmatched by the snap of a magnet or the electrical bonds that hold a single molecule together. And yet, gravity possesses a quality that the stronger forces do not. It is incredibly, infinitely patient. While other forces act in sudden bursts or tight local grips, gravity reaches out across the vastness of the void with a soft, persistent touch. It does not rush the birth of a star. It is content to wait for millions of years, working in the silence, nudging one atom toward another with the gentlest of hands. As you rest there, imagine this incredible patience. There is no hurry in the cosmos. Gravity works on a timeline that makes our human years seem like the blink of an eye. In the heart of the molecular cloud, gravity is simply waiting for the random movements of gas to bring a few extra atoms together. Once a small pocket of gas becomes just a tiny bit denser than the space around it, gravity's job becomes slightly easier. This small clump now has a slightly stronger pull, a slightly more persuasive call. It begins to draw in its neighbors, gathering more and more material into its quiet, steady embrace. This process of clumping is the first true architecture of the universe. It is a slow-motion gathering, a cosmic huddle where the cold, lonely molecules of the interstellar medium finally find one another. At first, these clumps are far too small to see, even if you were floating right beside them. But as the millions of years drift by, the density continues to rise ever so slightly. What was once a perfectly transparent mist, a ghost of a cloud that you could pass through without ever knowing it was there, begins to change its character. The cloud starts to thicken. It begins to develop a texture, a presence in the darkness. It is like watching a clear winter sky slowly fill with the soft, heavy weight of distant snow clouds. As the molecules pack closer together, they begin to interact with the light from the rest of the galaxy in a new way. The cloud is no longer invisible. It begins to catch the stray photons from distant, ancient stars, reflecting them in soft hues or, in some places, becoming so thick that it begins to block the light of the stars behind it, creating deep velvet shadows in the sky. You are witnessing the transition from a mere collection of gas into a majestic nebula. It is a visual manifestation of gravity's long, steady work. From a distance of trillions of miles, these structures look like towering pillars or soft, glowing veils draped across the dark. They are the cathedrals of the cosmos, built atom by atom over eons of time. And as gravity continues its work, pulling more and more matter into these central hubs, the scale of what is being created begins to truly reveal itself. These clouds are not just small pockets of gas. They are vast, sprawling landscapes that defy our earthly sense of distance. To truly understand the majesty of these cosmic cathedrals, we must try to grasp their scale, though the human mind often finds it difficult to hold such vastness. A single nebula can span hundreds of light years from one edge to the other. To put that into perspective, consider that a single light year is nearly 6 trillion miles, a 6 followed by 12 zeros. It is the distance light travels in a vacuum in 1 year, moving at an incredible 186,000 miles per second. If you were to board the fastest spacecraft ever built by human hands, it would still take you tens of thousands of years to cross just 1 light year. Now, imagine a cloud of gas and dust so immense that it stretches across hundreds of those units. These structures are so large that if you were standing in the middle of one, you might not even realize it. The gas is still thinner than any vacuum we can create on Earth, yet because the cloud is so incredibly deep, its cumulative presence becomes a masterpiece of form and color. It is only when we look at them from our distant vantage point on Earth that we can see them as a whole, as a singular, breathtaking object hanging in the void. As you lie there, let the sheer scale of the universe settle over you like a heavy, warm blanket. In the presence of something that spans hundreds of trillions of miles, our daily worries, our hurried schedules, and our small anxieties begin to feel very distant. They are like tiny ripples on the surface of a vast, still ocean. There is a profound peace in realizing how small we are in comparison to these giants, and how quiet the rest of the universe remains while it goes about the slow, patient business of creation. Take a slow, deep breath and feel yourself becoming a part of that stillness. You are safe in the vastness. Your only task right now is to exist, to breathe, and to listen. But even in this immense silence, these nebulae are not uniform or dull. They have individual characters, defined by the way they interact with the stars around them and the light that flows through the vacuum. Some are dark and cold, acting as silent sentinels of the deep, while others seem to burn with an internal fire, illuminating the dark with colors that no human eye could fully appreciate without help. The way a nebula presents itself to our telescopes depends entirely on the light that touches it and the specific elements hidden within its velvet folds. As we move deeper into these clouds, we begin to see that they are not just passive observers of the stars, they are active participants in a dance of light and energy. Starting with the most vibrant of them all, the clouds that seem to glow from within. These radiant clouds, the ones that seem to pulse with a light of their own, are known as emission nebulae. They are some of the most spectacular sights in the night sky, often resembling vast glowing gardens of light suspended in the dark. But they do not glow by magic. They glow because of a gentle, energetic conversation between the gas and the stars that live within or near them. Imagine a group of young hot stars that have recently flickered into life. These stars are incredibly powerful, pouring out intense amounts of high-energy ultraviolet radiation. As this invisible light travels through the surrounding clouds of gas, it encounters atoms of hydrogen, the simplest and most abundant element in the universe. When that high-energy light hits a hydrogen atom, it excites it. It gives the atom a little push, nudging its electrons into a higher energy state. But atoms, much like we do as we prepare for sleep, prefer to be in their lowest, most relaxed energy state. They want to be calm and still. So, almost immediately, the electron drops back down to its original level. As it does this, it releases that extra energy in the form of a tiny flash of light, a single photon. When trillions upon trillions of atoms do this all at once, across light years of space, the entire cloud begins to glow. It is a process very similar to how a neon sign works on a quiet street, or how a fluorescent bulb softly lights a room, but on a scale that is almost impossible to grasp. The most common color produced in these clouds is a soft, deep red. This specific shade is known to astronomers as hydrogen alpha emission. It is a warm, comforting hue, not a harsh red, but a gentle rosy glow that looks like the embers of a dying fire or the softest part of a summer sunset. Imagine this red light filling the void, acting as a cosmic nightlight for the developing stars tucked inside the cloud. It is a light that speaks of warmth, of energy being shared, and of the quiet, constant activity of the universe. As you visualize this soft red glow, let your mind drift through the mist. There is no heat here that could reach you. It is a glow born of physics and distance, a beautiful byproduct of light meeting matter. These emission nebula, like the famous Orion Nebula, are the nurseries where the universe is most active, Yet from our perspective, they appear as the most serene of portraits. You can imagine yourself floating weightlessly through this rose-colored fog, feeling the immense stillness of the gas as it hums with the energy of distant stars. However, not all clouds in the interstellar medium have the energy to glow with their own light. Some are more modest, content to simply catch the light of others and pass it along, in the same way that a mirror in a dark room doesn't create light but can still show you the way. There are regions of space that rely on the stars around them to reveal their presence. These clouds offer a different kind of beauty, a cooler, more ethereal sight that shifts our palette from the warm, earthy reds of the emission nebulae to something much more delicate, shimmering, and blue. These are the reflection nebulae. As the name suggests, they do not burn with their own internal energy or glow from the excitement of their atoms. Instead, they act like a fine cosmic mist catching the beams of distant brilliant stars. To understand how they look, imagine walking through a thick fog at night while a soft blue lamp glows nearby. The fog doesn't create its own light, but it catches that blue radiance, holding it in the air and spreading it out into a gentle, ethereal haze that seems to hang weightlessly in the dark. In the vastness of space, this happens because of a process called scattering. The clouds of reflection nebulae are filled with tiny grains of interstellar dust, microscopic pieces of carbon, silicates, and sometimes even ice. These grains are just the right size to catch and bounce shorter wavelengths of light. In the spectrum of visible light, blue has a shorter wavelength than red. So it is scattered much more easily. This is the very same scientific principle that gives Earth its beautiful blue sky. When you look up on a clear day, you are seeing sunlight being scattered by the molecules in our atmosphere. In a reflection nebula, we see that same peaceful blue scattered across trillions of miles of vacuum, creating a scene of profound serenity. One of the most famous examples of this is found around the Pleiades, a cluster of stars also known as the Seven Sisters. If you were to look through a powerful telescope, you would see these bright, young stars draped in what looks like delicate gossamer silk. This blue light isn't coming from the stars themselves, but from a cloud of dust that the stars happen to be passing through. It is a chance meeting in the dark. The dust catches the intense light of these hot stars and softens it, turning it into a shimmering, watery blue that looks like moonlight reflecting off a quiet pond in the middle of a forest. It is a light that feels cool to the touch, a visual breath of fresh air. As you imagine this scene, let yourself feel the stillness of that blue light. It is a color that suggests calm, quiet, and rest. Else, the light is not aggressive. It is filtered and gentle, reaching out through the darkness to show us the shapes of things that would otherwise remain invisible. It reminds us that even in the emptiest parts of the universe, there is a subtle beauty waiting to be revealed, provided there is a light nearby to show the way. These blue wisps look like frozen smoke, or the delicate threads of a spider's web caught in a morning frost. The blue veils of the reflection nebulae often sit right alongside the rosy glows of the emission nebulae we spoke of earlier, creating a palette of colors that rivals any sunrise on Earth. Together, they paint the cosmos in shades of lavender, magenta, and cerulean. But as we move further into these clouds, the textures change. The mist begins to thicken. The light which has been scattering and glowing so beautifully, starts to encounter regions where the dust is no longer a fine veil, but a heavy, impenetrable barrier. We are moving away from the light now, leaving the shimmering blues behind and traveling toward the parts of the nebula that keep their secrets tucked away in a deep velvet shadow. As we drift further into the heart of these interstellar clouds, the vibrant blues and soft pinks begin to recede, giving way to something quieter and more mysterious. We find ourselves entering regions where the light seems to simply stop. These are the dark nebulae, sometimes called absorption nebulae, and they are among the most striking features of our galaxy. To the early astronomers who first peered through their primitive telescopes, these patches looked like holes in the sky, voids where the stars had simply vanished. They called them coal sacks or black flags, believing they were looking at the very edge of the universe or into an empty abyss. But we have learned that these are not empty spaces at all. In fact, they are the very opposite. A dark nebula is a place of incredible abundance, where the cosmic mist has gathered so thickly that it forms a solid wall against the light. Imagine you are walking through a gentle evening fog that slowly grows thicker and heavier until you can no longer see the street lights behind you. This is what is happening here. The dust and gas have become so concentrated that they absorb and scatter all the visible light from the stars lying behind them, casting a long, deep shadow across the cosmos. Take a moment now to settle into the idea of this darkness. It is not a cold or frightening void, but a protective layer. Think of it as a heavy, dark velvet curtain that has been drawn across a window to keep out the morning sun. It is a place of profound stillness and privacy. Within these dark veils, the universe is keeping a secret, shielding its most delicate processes from the chaotic energy of the outside world. Just as you might pull a warm blanket up to your chin to feel secure and shielded from the room around you, these nebulae wrap themselves in shadow to create a sanctuary of perfect quiet. When we look at the Milky Way on a truly dark night, we can see these silhouettes clearly. They appear as long, dark rifts snaking through the bright band of our galaxy. One of the most famous is the Horsehead Nebula in the constellation of Orion. It is a towering pillar of dark dust that rises up like a shadow against a backdrop of glowing red gas. It is a magnificent silhouette, a reminder that the unseen parts of our universe are just as important as the parts that shine. These dark clouds are some of the coldest places in the galaxy, with temperatures hovering just a few degrees above absolute zero. In this deep, shivering cold, motion slows down. The frantic energy of the universe settles into a low, rhythmic pulse. In the safety of this dark embrace, something remarkable begins to happen. Because the light and heat from distant stars cannot penetrate the thick layers of the nebula, the interior remains undisturbed. It is here, in the heart of the shadow, that the building blocks of future worlds are being gathered. The darkness is not a sign of death, but a sign of preparation. It is a cosmic womb, a place where the chaotic elements of space are being organized into something new. As you lie there, feeling the weight of your own blankets, imagine the immense pressure and the perfect silence inside one of these dark veils. There is no wind here, no sound, and no stray light, to distract from the slow, patient work of gravity. The dust here is different from the dust we know on Earth. It is finer, older, and far more complex. It is the raw material of everything we have ever known, tucked away in the shadows, waiting for the right moment to begin its transformation. We are going to look closer at this dust now, peering through the dark to see what these tiny particles are actually made of and how they provide the foundation for the stars that will one day light up the night. Within these shadows, the space is filled with what astronomers call cosmic dust. But it is important to remember that this is not the kind of dust you might find on a bookshelf or tucked away in the quiet corners of a room. Earthly dust is made of common things, tiny fibers of fabric, bits of solar skin cells. Cosmic dust is far more ancient and far more pure. It is composed of tiny solid grains of silicates, which are essentially microscopic bits of rock, along with carbon, which is like the fine soot from a cooling fire, and various types of ice. Imagine a single grain of this dust. It is incredibly small, much smaller than the width of a human hair, even smaller than a single particle of smoke drifting from a snuffed candle. These grains are often jagged and irregular, and in the deep, shivering cold of the molecular cloud, they are often coated in a thin, translucent jacket of frozen water, methane, or ammonia. As you lie there, imagine these billions upon billions of tiny, icy diamonds drifting through the dark, each one a silent witness to the long history of the galaxy. These dust grains are not just floating aimlessly. They serve a vital purpose in the story of everything. In the extreme vacuum of space, atoms are very far apart. Without a place to meet, a hydrogen atom might drift for years without ever bumping into another. But these microscopic dust grains act as a landing pad, a quiet sanctuary for the elements. An atom of oxygen and 2 atoms of hydrogen can settle onto the cold, icy surface of a dust grain, find each other in the stillness, and bond together to form a molecule of water. It is here, on the surfaces of these tiny, frozen specks, that the complex chemistry of the universe begins. Simple elements are transformed into more intricate molecules, the precursors to the very water we drink, and the organic compounds that make up our own bodies. The dust acts as a cosmic laboratory, working in the perfect, lightless silence of the nebula to prepare the ingredients for future planets, and perhaps eventually the life that might one day walk upon them. As these grains gather more and more ice and more molecules, they begin to exert a subtle influence on their surroundings. They block the harsh, energetic radiation from distant, older stars, protecting the fragile molecules forming in their shadows. The cloud becomes denser, richer, and more complex. It is no longer just a thin mist. It is a heavy, laden atmosphere, thick with the weight of its own potential. The stillness we felt before is now coupled with a sense of quiet momentum. Every tiny grain, every frozen molecule is beginning to feel the collective pull of all its neighbors. The cloud is no longer just drifting. It is starting to lean inward. This gathering density is creating a subtle pressure, a tension between the desire to stay still and the inevitable pull of something much stronger. We are approaching a moment of transformation, a threshold where the gentle drift of the dust gives way to a more powerful, focused intention. The vast, dark cloud is preparing to fold in on itself, turning the silence of the void into the foundation of a star. This tension between the stillness of the gas and the persistent pull of gravity eventually reaches a very specific moment in time, a scientific threshold known as the gene's instability. It is a quiet, profound transition in the life of a nebula. Imagine, if you will, a delicate balance, like a feather resting on a silver scales. On one side you have the thermal pressure of the gas, the tiny vibrating movements of atoms that want to scatter, stay warm, and remain free. On the other side, you have the patient, unrelenting hand of gravity, trying to bring everything together into a single, focused point. For millions of years, these two forces may have lived in a peaceful stalemate. But as the cloud grows colder and the dust grows thicker, the balance begins to tip. When the cloud reaches a certain critical mass and density, the internal pressure can no longer support the weight of the gas above it. This specific point of no return is named after the physicist Sir James Jeans, who first mapped the mathematics of this cosmic surrender. It is the tipping point that marks the true beginning of a star's birth. In this moment, the equilibrium is lost. The cloud begins to give way, collapsing inward under its own immense weight. It is not a violent event, but a slow, graceful transition from a state of wandering to a state of purpose. You might think of it as the moment a heavy drop of rain finally detaches from the tip of a leaf, or the way a deep-held breath finally turns into a long, relaxing sea. The cloud has crossed a line from which there is no turning back. It has committed itself to the creation of something new. As you settle deeper into your covers, imagine this vast, dark expanse beginning to move. Because the nebula is so incredibly large, stretching across hundreds of light years, it does not collapse as one single, uniform piece. The cloud is not perfectly smooth. It is full of ripples, swirls, and pockets where the dust is just a little bit thicker or the gas is a little bit colder. As gravity takes hold, the cloud begins to fragment. It is a beautiful, silent process of division. The giant nebula begins to break apart into smaller individual clumps, much like a soft cloud of steam, dividing into smaller wisps or a sheet of ancient ice, gently spiderwebbing into 1,000 unique pieces. Each one of these fragments is now a world unto itself, a private pocket of darkness and potential. Each fragment is now acting independently of the rest of the cloud, driven by its own internal gravity, beginning its own long, solitary journey toward the light. The giant wandering mist is transforming into a nursery filled with thousands of individual hearts, all beating to the slow, rhythmic pulse of the collapsing dark. As these fragments continue to separate, we begin to see the true nature of a stellar nursery. It is rarely a solitary event. When a giant molecular cloud collapses, it doesn't give birth to just a single, lonely sun. Instead, the process is communal, a shared beginning that spans across the light years. This one vast, dark cloud, this silent ocean of gas and dust, can fragment into hundreds, sometimes even thousands, of smaller, dense cores. These new stars, born from the same parent cloud at the same moment in time, form what astronomers call an open star cluster. It is a family of stars, all siblings of the same age, composed of the same ancient materials, beginning their long lives together in the quiet dark. You might imagine them like a group of lanterns being lit one by one across a vast dark field, each one adding a soft, gentle glow to the neighborhood. One of the most famous examples of such a family is the Pleiades, often called the Seven Sisters, which you can see in the night sky as a tight, sparkling knot of blue light. Those stars were once fragments just like the ones we are imagining now, drifting together, born from the same cosmic breath. Take a slow, deep breath and let your mind rest on this image of companionship. Even in the immense, silent stretches of space, there is a sense of belonging. These stars will travel together for millions of years, held close by their mutual gravity, before they eventually drift apart to find their own paths through the galaxy. But for now, in this early stage, they are safe, surrounded by their kin in the velvet darkness of the nebula. It is a peaceful, unhurried start to a journey that will last for eons. As you feel the weight of your body pressing into your mattress, let your awareness narrow down. We are moving away from the grand scale of the entire cluster, drifting past the thousands of other forming stars. We are focusing our attention on just one of these fragments. It is a small, dark pocket of gas and dust, perhaps only a few times larger than our own solar system will eventually become. It looks like a soft, shadowy marble suspended in the mist. As this specific fragment continues to shrink under the weight of its own gravity, something subtle begins to change. The fragment is no longer just falling inward. It is beginning to move in a new way. It is finding its own rhythm. Very slowly at first, almost imperceptibly, this dark knot of gas begins to spin. It is a gentle rotation, a silent pirouette in the dark. This motion is not accidental. It is the beginning of a transformation that will shape everything this star is destined to become. The stillness of the cloud has been replaced by a quiet, rhythmic movement, like the slow turning of a great, invisible wheel. As our fragment of the nebula continues its inward collapse, a fundamental rule of the universe takes hold. It is a principle called the conservation of angular momentum. You can think of it as the universe's way of keeping track of motion, ensuring that the energy of a spin is never truly lost. As the cloud draws its mass closer to its center, shrinking from a vast loose cloud into a tighter, more compact sphere, it must, by necessity, begin to spin faster. Imagine, if you will, a figure skater performing a beautiful, slow-motion scene on a mirror-like sheet of ice. At first, their arms are stretched out wide, and their rotation is graceful and leisurely. But as they begin to pull their arms in close to their chest, drawing their weight toward their center, their body begins to spin faster and faster, even though they haven't added any extra energy. The motion is simply drawn inward, concentrated into a smaller, tighter space. The star-to-be is doing exactly the same thing. What was once a lazy, drifting motion in the vastness of the nebula is now becoming a steady, rhythmic whirl. It is a quiet, powerful momentum that governs the birth of every star in the sky. As the rotation speeds up, another change begins to occur. The centrifugal force, the same outward tug you might feel on a spinning playground carousel, begins to fight against the pull of gravity, but it only does so along the equator of the spinning cloud, while the top and bottom of the cloud, the poles, can still fall straight inward toward the center. The material at the sides is held back by the speed of the spin. Slowly, the spherical cloud begins to flatten. It loses its roundness, stretching out into a wide, elegant disk, much like a ball of dough being gently tossed and spun into a thin circle. This is what astronomers call a protoplanetary disk, a flat, rotating plateau of gas and dust that surrounds the growing center. It is a shape that appears everywhere in our universe, from the rings of Saturn to the great spiral arms of the galaxies themselves. It is a shape of balance and order, a cosmic cradle. In the very heart of this spinning disk, the density is rising rapidly. The atoms of hydrogen and helium are no longer drifting far apart. They are being packed together, closer and closer. They begin to bump into one another, rubbing and jostling in the increasingly crowded space. This constant interaction creates friction, and with friction comes a new sensation in the cold dark of space: warmth. The center of the disk is starting to glow with a faint, invisible heat. The deep, biting cold of the interstellar medium is being pushed back by the kinetic energy of the collapse. Gravity is squeezing the gas so tightly that the temperature begins to climb, degree by degree, turning the core into a sanctuary of warmth amidst the freezing void. This gathering heat is the first sign that something incredible is about to happen, a signal that the darkness is preparing to give way to light. At this stage of our journey, we call this glowing, concentrated center a protostar. The word proto comes from the Greek for first, and in many ways, this is the first true version of the star we are beginning to see. It is an infant, still tucked away in the nursery of the nebula, but its presence is undeniable. The protostar is like a cosmic magnet, drawing in the surrounding material from that flat, spinning disk we imagined earlier. It is still growing, still feeding on the gas and dust that remains in its neighborhood, slowly pulling every nearby atom into its warm embrace. It is important to remember that, at this moment, the protostar is not yet a true star. The nuclear fire that powers the sun has not yet been lit. There is no fusion happening in its core quite yet. Instead, all of the warmth and light it produces comes from the sheer force of its own weight, the energy created by billions of tons of gas falling inward, and the friction of atoms rubbing together under immense pressure. It is fueled by gravity alone. Think of it as a great, warm heart beating in the center of a quiet storm, a reservoir of potential waiting for the right moment to awaken. But if you were to look at this area with your own eyes, you might not see anything at all. The protostar is shy, hiding behind a thick, dark veil of gas and dust. Astronomers often call this a cocoon, and it is a very fitting name. Just as a silkworm wraps itself in a protective layer while it transforms, the protostar is enveloped in a dense cloud that blocks almost all visible light. To a casual observer, this part of the nebula might look like a dark smudge, a shadow, or a hole in the tapestry of the stars. It is a place of deep velvet mystery. Inside that cocoon, however, the temperature is rising steadily. Because the protostar isn't yet hot enough to shine with the brilliant white or yellow light of a mature star, it glows in a different way. It radiates infrared light, a soft, invisible glow that we perceive not as a shimmer, but as heat. It is a gentle, pulsing warmth, vibrating out through the dust. It is the same kind of warmth you might feel from a smooth stone that has been sitting in the sun all day, or the lingering heat from the embers of a fireplace long after the flames have died down. Imagine yourself drifting near this cocoon, feeling that subtle, rhythmic warmth through the darkness. It is a peaceful, steady heat, a sign of life forming in the deep cold of space. For a very long time, these early moments of a star's life remained a secret, hidden away from our view. To the telescopes of the past, these nurseries looked like empty voids or impenetrable walls of soot. But as we have learned more about the universe, we have found ways to look through the veil. We have developed special ways to see the heat hidden behind the dust, allowing us to witness the secret, quiet beginnings of stars that would otherwise remain invisible to us in the dark. To peer through these thick curtains of dust, we rely on a different kind of sight called infrared astronomy. While our own eyes are tuned to see the colors of the rainbow, the universe speaks in many other languages of light. Some of these waves are short and easily blocked, while others are long and slow, able to slip through the gaps between dust particles like a gentle breeze passing through a screen door. This is the realm of the infrared, the light of heat. Instruments like the James Webb Space Telescope act as our quiet, patient observers in the dark. They are designed to catch these long, gentle waves that have traveled for thousands of years across the vastness of space. When we look at a nebula through an infrared lens, the view changes completely. Places that once looked like impenetrable walls of black soot suddenly become transparent and ethereal. The dust that usually hides the secrets of the universe becomes almost invisible, allowing us to look deep into the heart of the stellar nursery. Consider the famous pillars of creation, those towering clouds of gas and dust in the Eagle Nebula. In ordinary light, they appear as solid, majestic monuments, dark and mysterious, against the golden backdrop of space. But when we look with infrared eyes, the pillars become ghostly and translucent, like a soft blue-tinted fog. And inside that fog, we see them, thousands of sparkling, brilliant points of light, shimmering like diamonds scattered on velvet. These are the protostars and young suns that were hidden from us for so long. It is as if a heavy velvet curtain has been pulled back, revealing a crowded, vibrant nursery where we once thought there was only shadow. Take a moment now to find an even more comfortable position. Close your eyes and take a slow, deep breath. Imagine you are floating in the profound stillness of that nebula. Everything around you is dark and cool, but you can feel a subtle, comforting radiance against your skin. Even though you cannot see the source of this light with your eyes, your body recognizes its presence. You are sensing the warmth of a star being born. This heat is a signal, a quiet heartbeat pulsing through the void, telling the story of a new beginning. It is a reminder that in the universe, as in life, much of what is most important happens beneath the surface, hidden away until the moment is right. Just as we use these powerful telescopes to see the hidden warmth of the cosmos, we can use our own quiet focus to feel the connection between the cold, distant reaches of space and the gentle heat of our own existence. We are made of the same materials, governed by the same laws of nature. There is a peace in knowing that even in the deepest shadows of the galaxy, there is something growing, something gathering energy and light. Back in our cosmic nursery, the protostar we have been following continues its patient, ancient work. It is no longer just a small clump of gas. It has become a massive, glowing sphere, still shrouded in its dusty cocoon, but growing more powerful with every passing moment. As it pulls in more and more material from the surrounding disk, its gravity becomes even stronger, and the pressure at its center begins to climb to unimaginable levels. The atoms at the very heart of the sphere are being squeezed closer and closer together, vibrating with an intensity that will soon change the very nature of this object. The temperature is rising, moving steadily toward a critical point, a threshold where the simple heat of friction will give way to a much greater, much older power that fuels the stars for billions of years. The temperature at the heart of our young protostar has been climbing steadily, fueled by the relentless weight of the gas and dust pressing down from above. Within this deep hidden core, the conditions are becoming extreme. The hydrogen atoms, which have been swirling and colliding in the dark for millions of years, are now packed so tightly together that they are moving at incredible speeds. They are vibrating with a frantic, invisible energy, seeking a way to release the tension of the crush. Imagine the density there. A place where matter is squeezed so firmly that it begins to lose its familiar identity, becoming a sea of charged particles, all waiting for a single, transformative moment. And then it happens. A threshold is crossed. The temperature hits 10 million degrees Celsius, a number so vast it feels like a dream of heat. At this precise moment, the very nature of matter changes. The hydrogen nuclei, which naturally want to push away from one another due to their shared positive charges, can no longer resist the overwhelming pressure. They are forced together, merging and transforming into helium. This is the spark of nuclear fusion. It is the true birth of a star. In an instant, a tremendous burst of energy is released from the core, radiating outward in waves of light and heat. It is a silent explosion of life that will sustain the star for eons to come. This outward surge of energy creates a powerful internal pressure, and it is here that we witness one of the most beautiful balances in the natural world. For millions of years, gravity has been the undisputed master of this cloud, pulling everything inward tighter and tighter. But now, the star has found its own strength. The outward pressure from the nuclear fire at the center begins to push back against the inward pull of gravity. These two monumental forces, the crushing weight of the star's mass and the radiant energy of the fusion, reach a state of perfect, quiet agreement. Scientists call this state hydrostatic equilibrium. It is a cosmic handshake, a moment where the star stops its long million-year collapse and settles into a stable, enduring form. The star is no longer shrinking. It has found its shape, its size, and its steady rhythm. It is like a deep, long breath that is finally held in perfect stillness. The star has reached the main sequence, the long, steady middle age of its life. In this state of equilibrium, the star becomes a reliable source of light in the darkness. It is no longer a chaotic, dusty nursery, but a beacon, a fixed point of warmth in the cold expanse of space. Take a slow, deep breath and imagine that sense of balance within yourself. The feeling of everything finally clicking into place, of tension finding its release in a steady, calming glow. The star is now at peace, its internal fires burning with a rhythmic consistency that can last for millions or even billions of years. It has moved from the struggle of birth into the serenity of existence. However, the stars that are born from these clouds are not all the same. Some are massive and brilliant, burning through their fuel with a fierce, short-lived intensity that lights up the entire galaxy. But most of the stars in our universe are much more modest. They are the quiet ones, the ones that do not seek the spotlight of the cosmos, but instead provide a slow, steady warmth that outlasts almost everything else. As we move away from the general process of stellar birth, let us focus our attention on the most common and perhaps the most comforting type of star in existence. While our own sun is a bright yellow-white beacon, the vast majority of the stars in the night sky belong to a different family entirely. They are the small, steady, and incredibly long-lived stars known as red dwarfs. These humble stars represent the true endurance of the cosmos, and it is to their soft crimson light that we now turn our gaze. To understand the red dwarf, or the M dwarf, as it is known in the formal language of astronomy, we must first adjust our expectations of what a star can be. We often think of stars as grand, blinding powerhouses of light. But the red dwarf is something far more subtle. It is the quietest member of the stellar family, a star that has chosen a path of moderation and extreme patience. If the universe were a vast, darkened landscape, these stars would not be the roaring bonfires or the sweeping searchlights. Instead, they would be the small, glowing embers of a campfire that has settled into a deep, rhythmic burn. A light that does not demand your attention, but offers a constant, reliable warmth to those who are close enough to feel it. These stars are the smallest and coolest of all the main sequence stars, those stars that, like our sun, are currently fusing hydrogen into helium. In the world of stellar classification, they are given the letter M, a category that represents the lower end of the temperature scale. But do not let the word cool mislead you. In the context of the cosmos, this is a relative term. While their surfaces are thousands of degrees, they are significantly less intense than our own sun. Because they are cooler, the light they emit is shifted toward the longer, redder end of the spectrum. When you imagine a red dwarf, do not picture a harsh, blood-red sphere. Instead, visualize a soft, deep orange-red glow, the color of a sun that is perpetually setting, caught in that final golden-red moment before the twilight takes over. It is a gentle, soothing hue, a cosmic nightlight that bathes its surroundings in a color that feels ancient and restful. Because they are so small and operate at such low temperatures, red dwarfs are incredibly dim. If you were to place one of these stars side by side with our sun, it would look like a tiny glowing coal next to a brilliant spotlight. In fact, many red dwarfs emit less than 1% of the light that our sun produces. This is why, despite being the most numerous stars in the sky, not a single red dwarf is visible to the naked eye from Earth. They are the hidden residents of the night, the silent majority that populates the darkness between the brighter, more famous constellations. They are content to remain in the shadows, burning with a precision and a steadiness that more massive stars simply cannot achieve. This steadiness is perhaps their most beautiful quality. While larger stars can be temperamental, pulsing and heaving with internal instability, a mature red dwarf is a model of consistency. It hums with a low-frequency energy, a steady heartbeat that stays the same for age after age. As you lie there, drifting closer to sleep, you might imagine the comfort of such a presence, a light that never flickers, a heat that never wavers, a star that simply exists, quietly and faithfully, in the vastness of the void. They are the most common type of star in existence, outnumbering all other types of stars combined. Everywhere we look in our galaxy, in every corner and every cluster, these small red lanterns are there, outlasting the giants and providing a foundation of light for the entire universe. They are a true endurance of the cosmos, and as we look closer at their numbers, we begin to see just how much of our galaxy is actually built upon their humble, crimson shoulders. When we look up at the night sky, we often see the giants, the bright, flashy stars that demand our attention and define the constellations we know so well. But the reality of our galaxy is much more modest and much more peaceful. Astronomers estimate that roughly 3/4 of all the stars in the Milky Way are red dwarfs. Out of the hundreds of billions of stars that make up our spiraling home, 75% belong to this quiet, diminutive class. It is a staggering thought to hold in your mind as you drift toward sleep. The stars we know by name, Sirius, Rigel, Betelgeuse, are the rare exceptions, the luminous anomalies of the cosmos. The red dwarfs are the rule. They are the silent majority, the background hum of the universe. Because they are so dim, they do not crowd the sky with glare. Instead, they fill the galaxy with a soft, pervasive presence that we can only detect with our most sensitive instruments. They are everywhere, tucked into the folds of the spiral arms, yet they never raise their voices. Take a slow, deep breath. Feel the weight of your body against the mattress, and let the vastness of these numbers settle over you like a warm, heavy blanket. There is a profound sense of security in knowing that the universe is not just a place of violent explosions and blinding light, but a place filled with these small, enduring neighbors. We are cradled in a galaxy that favors the small and the steady. Imagine yourself floating in a sea of these gentle, crimson lights, millions upon millions of them, spaced out across the dark, each one a tiny, reliable hearth in the cold of space. You are part of a very crowded yet very quiet cosmic neighborhood. There is no need for urgency here. These stars are in no rush, and neither are you. To understand why they are so common, we have to look at their physical nature. To call them small is scientifically accurate, but it is hard to grasp the scale without a point of reference to ground the imagination. If you were to imagine our sun as the size of a large glowing beach ball, a typical red dwarf would be no larger than a small orange, or perhaps even a lime. They exist on a scale that feels almost approachable, almost familiar. This compact nature is not a weakness. It is the very secret to their survival. While the massive steers of the universe are like great bonfires that roar and crackle, consuming their wood in a single intense night, the red dwarf is like a single steady ember, tucked deep within the ash, glowing softly and providing warmth for a time so long it is almost impossible to measure. As we move closer to these tiny lanterns, we can see how their modest mass defines everything about their long, tranquil lives. When we talk about the mass of a red dwarf, we are looking at the very edge of what it means to be a star. In the grand hierarchy of the cosmos, these objects sit right at the boundary between the planets and the suns. To be classified as a red dwarf, a star typically possesses between 7.5% and 50% of the mass of our own sun. It is a modest amount of material, yet it is exactly enough to perform the miracle of nuclear fusion. If a star were any lighter than that lower threshold of 7.5%, it would never become a star at all. It would remain a brown dwarf, a failed star that glows dimly from its own birth heat but never manages to ignite the hydrogen in its core. But the red dwarf just barely makes the cut. It has just enough gravity, just enough weight to press down on its center with the necessary force to begin its long, slow burn. To help visualize this, think of the planet Jupiter, the undisputed king of our solar system. Jupiter is enormous, a gas giant so large that all the other planets could fit inside it twice over. And yet, Jupiter is still far too small to be a star. If you were to take 80 Jupiters and stack their mass together into a single sphere, you would finally have enough material to create the smallest possible red dwarf. There are stars out there, drifting quietly through the dark, that are only about 10 or 20% larger in diameter than Jupiter. If you saw one of these stars and the planet side by side, they might look like twins in size, but their hearts would be entirely different. While Jupiter is cold and quiet at its core, the red dwarf is alive with the soft, steady pressure of fusion. It is a true star, a self-sustaining engine of light despite its diminutive stature. As you lie there, feeling the quiet rhythm of your own breath, consider how this lack of bulk is actually a profound advantage. In our world, we often think of bigger as better or stronger, but in the life of a star, mass is destiny, and too much mass is a heavy burden. The giant stars of the universe are trapped by their own weight. They must burn through their fuel at a frantic, violent pace just to keep from collapsing under their own gravity. They are spectacular, yes, but their lives are fleeting, over in a cosmic blink of an eye. The red dwarf, however, possesses a secret superpower, its smallness. Because it has so much less mass pressing down on its core, the temperatures and pressures inside are much lower than those in the sun. It doesn't have to fight nearly as hard to stay balanced. It can afford to be frugal. It sips at its hydrogen fuel like a delicate tea rather than gulping it down like a roaring furnace. This economy of scale is what allows the red dwarf to outlast everything else in the sky. By being small, it avoids the frantic race toward exhaustion. It settles into a pace that is calm, sustainable, and incredibly enduring. It is the tortoise of the celestial world, moving slowly but surely through the eons, while the hairs of the galaxy burn out and fade away. This modest mass is the foundation for a life that spans almost the entire history of time itself. It is a quiet strength, born from having just enough and nothing more. In the stillness of the night, there is a deep comfort in the idea that the most enduring things in the universe are often the ones that started out the smallest. If we could look deep inside the heart of a star like our sun, we would see a structure made of distinct layers, almost like the rings of an ancient tree. In the sun, there is a vast, dense middle layer called the radiative zone. It is a region so packed with matter that light and energy can take hundreds of thousands of years just to soak through it. This layer acts like a wall, preventing the hydrogen on the outside of the star from ever reaching the nuclear furnace at the very center. It means that even when the sun eventually begins to fade, it will still have a massive reservoir of unused fuel sitting in its outer layers, forever out of reach of the core. The red dwarf, however, is built with a much simpler and more elegant design. Because it is smaller and the pressure is less intense, it doesn't have that middle barrier. Instead, the entire star is what scientists call fully convective. To understand what this means, imagine a pot of thick, delicious soup simmering very gently on a low flame. As the soup at the bottom of the pot warms up, it becomes lighter and slowly rises to the surface. There, it releases a little bit of its heat into the air, cools down, and then gracefully sinks back to the bottom to be warmed once again. This is exactly what is happening inside a red dwarf. The star is constantly, patiently stirring itself. The hydrogen at the very surface isn't just sitting there. It is being pulled into a slow, rhythmic dance, carried down into the glowing depths of the core. Once it reaches that warm center, it takes its turn in the process of fusion, and then the energy it creates helps carry it back toward the surface. It is a perfect, continuous loop of recycling that never stops. This internal motion makes the red dwarf one of the most efficient machines in the entire universe. While a larger, more complex star might only burn through a small fraction of its total hydrogen before it reaches the end of its life, a red dwarf uses every single drop. It leaves nothing to waste. It is as if the star is constantly tending its own hearth, making sure every ember is moved to the center of the fire to keep the light going. As you lie there, feeling the weight of your blankets and the stillness of the room, you can imagine this slow, fluid churning happening in the deep silence of space. It is not a violent or chaotic movement, but a graceful, rolling circulation that happens over vast stretches of time. This total efficiency, this ability to use every bit of its being to sustain its glow, is the true secret to the red dwarf's endurance. When you combine a very frugal, low rate of burning with a mechanism that provides a never-ending supply of fresh fuel to the core, you create a star that can stay lit for a duration that defies human comprehension. This quiet, internal stirring is the foundation for a life that will span the rise and fall of countless other worlds. This incredible efficiency, this patient and thorough use of every atom of hydrogen grants the red dwarf a lifespan that is truly staggering. When we look at the stars in the night sky, we often think of them as eternal. But most of the brilliant stars we see are actually quite fleeting. They burn bright and hot, consuming their fuel in a reckless rush, lasting only a few million years before they fade away. Even our own sun, which provides such a steady and reliable presence in our lives, has a finite journey. It is expected to shine for a total of about 10 billion years, a vast amount of time by any human standard. But a red dwarf operates on a completely different scale of existence, because it burns its fuel so incredibly slowly, and because that gentle, internal stirring keeps the core constantly supplied with fresh hydrogen. A red dwarf doesn't just outlive the larger stars. It outlives them by a margin that is difficult to even imagine. While our sun might live for 10 billion years, a small red dwarf can continue to glow steadily for trillions of years. Trillions. It is a number that feels like a deep, endless ocean. To put it in perspective, a red dwarf can live up to 1,000 times longer than our sun. If the entire lifespan of the sun were condensed into a single week, a red dwarf would continue to shine for nearly 20 years. It is the ultimate marathon runner of the cosmos, pacing itself with such care that it will still be shining long after the sun is cooled, and the larger, more famous constellations have vanished from the sky. As you rest here, let that thought bring a sense of profound stability to your mind. We often hear about the vastness and the changes of the universe, but the red dwarf reminds us that there is also a deep, quiet permanence. These stars are the steady anchors of the galaxy. They are not in a hurry. They do not flicker or fade with the passing of eons. They simply exist, casting their soft orange-red light into the darkness, providing a reliable foundation for whatever worlds might circle them. In a universe that can sometimes feel fast-moving or unpredictable, the red dwarf is a symbol of endurance. It tells us that the lights of the universe will stay on for a very, very long time. There is no rush, no urgency in the life of such a star. It has all the time in the world and more. You can almost feel that sense of timelessness settling over you now. The idea that the most common stars in existence are also the most patient. They are the quiet sentinels that will witness the unfolding of the distant future long after the current era of the universe has passed. Knowing they are there, burning with such steady and reliable grace, allows us to let go of the day and sink into a deep, untroubled rest, held by the knowledge that the cosmos is a place of enduring light and long, peaceful silences. The universe is not a place of sudden endings, but of incredibly long, slow transitions. These stars ensure that the galaxy remains a home for light and warmth, for a duration so long it is practically indistinguishable from forever. There is a deep comfort in that longevity, a reminder that the most important things in the universe are built to last. This incredible longevity is tied to what astronomers call the main sequence. You can think of the main sequence as the long, stable prime of a star's life. It is the period when a star is successfully fusing hydrogen into helium in its core. maintaining a perfect, graceful balance between the inward pull of gravity and the outward pressure of its own light. For a star like our Sun, this stage is a relatively brief 10 billion years. Eventually, the Sun will consume the hydrogen in its core and begin a series of dramatic changes, swelling into a red giant and leaving the main sequence behind. But the red dwarf is different because it is so small and its internal processes are so efficient. It stays on the main sequence for practically its entire existence. It does not experience the midlife crises of larger stars. It does not swell or fluctuate wildly. It simply stays. To a red dwarf, the main sequence isn't just a phase, it is nearly the entire story. Because the universe is only about 13.8 billion years old, every single red dwarf that has ever been born in the history of the cosmos is still in the very beginning of its life. Not a single one has ever grown old. Not a single one has ever died of old age. They are all still there, shining with the same steady orange-red glow they had when they first ignited billions of years ago. Take a slow, deep breath now and let your body sink a little deeper into the softness of your bed. As you exhale, imagine that steady, unchanging light. While the rest of the universe goes through cycles of birth and dramatic change, while galaxies collide and giant stars explode in brilliant supernovae, these small stars remain exactly as they are. There is a profound peace in that kind of consistency. You don't have to worry about the light flickering or the environment shifting. It is a constant, reliable presence that has been there since the early days of the galaxy and will be there long after the distant future has become the ancient past. Think of the red dwarf as a quiet lamp in a vast, dark library. It doesn't need to be the brightest light in the room to be the most important one. Its value lies in its persistence, in its refusal to go out. It provides a sanctuary of stability in a universe that is always in motion. As you drift closer to sleep, let the stillness of these stars mirror the stillness in your own room. Everything is as it should be. The lights of the cosmos are steady, patient, and enduring. It is easy to think of these stars as distant, abstract concepts, tiny lights hidden in the far reaches of the Milky Way. But these quiet neighbors are much closer than you might realize. They are not just scattered in far-off nebulae. They are right here, in our own celestial neighborhood. In fact, if we were to look out from our own solar system and seek out our very nearest stellar companion, we wouldn't find a giant, blazing sun or a complex system of multiple bright stars. Instead, we would find one of these humble, enduring red dwarfs, waiting just across the cosmic street, a silent sentinel in the nearby dark. That star, our closest companion in the silent void, is known as Proxima Centauri. The name itself means the nearest of Centaurus, a fitting title for a neighbor that sits just 4.2 light years away. To put that distance in perspective, imagine a beam of light, the fastest thing in the universe, leaving that small red star tonight. It would travel through the silent, freezing vacuum of space for over 4 years before finally reaching your eyes. In the grand tapestry of the Milky Way, which spans over 100,000 light years, 4 years is nothing more than a heartbeat. It is the cosmic equivalent of living in the house right next door, just across a narrow, quiet street. Yet, despite this incredible proximity, Proxima Centauri is a shy neighbor. If you were to step outside on a perfectly clear dark night and look toward the southern sky, you would not see it. It is entirely invisible to the naked eye, while its sister stars in the same system, Alpha Centauri A and B, shine brightly enough to be seen from Earth as a single brilliant point. Proxima is too small and too cool to announce itself so loudly. It is a star that requires patience and technology to find. Through the lens of a powerful telescope, it appears not as a blazing furnace, but as a tiny ruby-red dot, huddled against the vast velvet blackness of the background. It is a humbling thought to realize that the star closest to our home is one we cannot even see without help. It reminds us that the universe is full of hidden wonders, things that exist and thrive even if they don't demand our attention with blinding brightness. Proxima Centauri is content to glow with its modest orange-red light, burning its fuel with a slow, careful precision that ensures it will outlive almost every other star we can see in the night sky. If the sun were a roaring bonfire, Proxima Centauri would be a single, glowing coal, smaller, cooler, but capable of holding its heat for a much, much longer time. As you lie there, perfectly still, imagine the quiet of that space between us and Proxima. It is a long, dark corridor, but it is not empty. We have discovered that this small, dim star is not traveling alone through the galaxy. Like a parent holding on to the hands of its children in the dark, Proxima Centauri carries its own family of planets. These worlds are nestled close to their parent star, huddled into its soft, dim warmth. And as we look closer at these planets, we begin to wonder what life might be like on a world where the sun is not a bright yellow circle, but a large, deep red orb that hangs heavy in the sky, providing a perpetual twilight glow. These planets exist in a unique balance, governed by the gentle temperament of their small, steady star. When we look at these small red stars, we often ask the same question we ask of the great bright ones. Could someone or something live there? For life as we know it to exist, a planet needs to be in a very specific place, a region astronomers call the habitable zone. You might know it by a simpler, more comforting name, the Goldilocks zone. It is the area around a star where the temperature is just right, not so hot that oceans would boil away into steam, and not so cold that they would freeze into solid, silent ice. It is the place where water can remain a liquid flowing gently across the surface of a world. In our own solar system, the sun is large and hot, so the Earth must stay at a respectful distance to remain comfortable. We sit nearly 93 million miles away, enjoying the bright yellow warmth from afar. But a red dwarf is different because it is so much smaller and cooler. Its habitable zone is pulled inward, drawn tight toward the star like a warm blanket. To catch enough heat to keep its water liquid, a planet must huddle incredibly close to its red sun. If the Earth were moved to the habitable zone of a red dwarf, it would be so close that the star would appear huge in the sky, a massive, glowing ember filling the horizon. Imagine a planet like Proxima Centauri b, which rests in this cold, narrow band. It orbits its star at a distance that is only a tiny fraction of the distance between the Earth and the Sun. In fact, it is much closer to its star than the scorched planet Mercury is to our Sun. Because the distance is so small, The planet completes its journey around the star, its entire year, in just about 11 Earth days. Time moves differently there. The seasons, if they exist, pass in the blink of an eye. Yet, despite this proximity, the environment on the surface would not feel hurried. It would likely feel incredibly still. On such a world, the light would be unlike anything we experience here. Our sun bathes us in a brilliant white gold light that turns our sky a vibrant blue. But on a planet orbiting a red dwarf, the sky would likely take on deeper, moodier hues. The light provided by a red dwarf is rich in infrared and deep reds. If you were to stand on the surface of this distant world, the sun would not be a small blinding coin in the sky. It would be a large, soft-edged orb of crimson, hanging low and heavy. The plants, if they had evolved to soak up this specific kind of light, might not be green. They might be dark, perhaps even black or deep maroon, designed to absorb every bit of the gentle energy the red star provides. There is a profound sense of intimacy in this arrangement. The planet and the star are locked in a close, eternal embrace. Because they are so near to one another, the gravity of the star exerts a powerful, steady pull on the planet, much like the way our moon is held by the Earth. This closeness creates a unique phenomenon, a profound stillness that defines the very nature of the world. It is a place where the sun doesn't move across the sky in the way we are used to, but instead finds a fixed position and stays there, watching over the landscape with an unblinking ruby eye. As you settle deeper into your covers, imagine a world where the day never ends and the sun never sets, held in place by the silent, invisible hands of gravity. This phenomenon is known as tidal locking. Just as our moon always shows the same face to the Earth, gravity has gently reached out and slowed the rotation of these close-in planets until they are perfectly synchronized with their orbit. It is a slow, rhythmic process of cosmic friction that takes millions of years to complete, eventually settling the planet into a state of permanent stillness. On a world like this, the concept of a day as we know it, a cycle of light and dark, simply does not exist. Instead, the planet is divided into two eternal halves, each experiencing a different version of forever. One hemisphere is bathed in a perpetual noon. The red sun sits stationary in the sky, never rising and never setting. It remains fixed, a constant source of warmth and soft ruby light. In this half of the world, the sun is an ever-present guardian, its light filtering through the atmosphere in a steady, unwavering stream. On the opposite side of the world, there is a land of eternal night. Here, the distant stars are the only companions, shining with a crisp, cold brilliance in a sky that never knows the dawn. It is a place of deep, silent shadows and infinite starlight, a world tucked away in a perpetual velvet slumber. But between these two extremes lies a thin, circular ribbon of land known as the Terminator Line. It is the twilight zone, a ring that encircles the entire planet, where the sun is forever perched on the horizon. If you were to stand along this line, you would find yourself in a place of perfect, unchanging balance. The sky would be a constant painted masterpiece of deep violets, burnt oranges, and soft magentas. The sun would not be a blinding circle, but a gentle, glowing arc, half hidden by the curve of the world, as if it were perpetually tucking itself into bed. In this place, the shadows are long and soft, and they never move. There is no rush to beat the sunset, because the sunset never ends. You could sit in the cool grass for 1,000 years, and the light would remain exactly as it is, an eternal golden hour that cradles the landscape in a warm amber glow. There is a profound peace in a world without clocks, where time is not measured by the movement of the sun, but by the slow, steady pulse of the planet itself. In our world, we are often chasing the light or retreating from the dark. We measure our lives in the ticking of seconds and the passing of days. But on a tidally locked planet, the environment is static and patient. It offers a sense of permanence that is hard to find elsewhere. The air in the twilight zone remains cool and still, a gentle bridge between the warmth of the dayside and the chill of the night. It is a world that has reached its final, restful state, held firmly in the gravitational embrace of its star. As you lie there, imagine the silence of that twilight world. There is no wind born of changing temperatures, no sudden shift in the weather as the sun goes down. There is only the steady, unmoving light of the red dwarf casting its soft, protective glow over the horizon. It is a reminder that even in the vastness of space, there are places of absolute stability, sanctuaries of stillness, where the universe seems to hold its breath. Take a long, slow breath of your own, and let the idea of that eternal, unchanging sunset settle over you like a heavy, warm quilt. Within this stillness, the star and its planet exist in a deep rhythmic harmony that spans across the eons. While the view from the terminator line of such a planet feels like the very definition of permanence, the star itself has its own journey of settling into stillness. In their earliest years, red dwarfs are known for being somewhat spirited. In the youth of the universe, and in the youth of their own long lives, these stars can be quite active. They possess powerful magnetic fields that occasionally snap and tangle, sending out flickers of light known as stellar flares. These are like the sudden, bright thoughts of a young mind, energetic and brief, illuminating the darkness with a quick, brilliant flash before receding once more into the orange glow. But the beauty of the red dwarf lies in its patience. As millions and then billions of years pass, the star begins to mature. It sheds that youthful restlessness, its magnetic fields softening, and its rotation slowing to a graceful, measured pace. It moves out of its active phase and enters a period of profound legendary stability. While larger stars like our sun eventually grow restless and expand, the red dwarf simply settles deeper into its quiet work. It becomes one of the most stable objects in all of creation, a steady, unwavering lantern that does not flicker, does not fade, and does not falter. Close your eyes for a moment and imagine this transition. Think of a fire that has been burning for a long time. At first, there are sparks and the occasional crackle of wood, but as the night deepens, it becomes a bed of glowing embers. These embers do not jump or snap. They simply radiate a constant, reliable warmth that fills the room. This is the mature life of a red dwarf. It is a star that has found its rhythm, a slow and steady heartbeat that will continue unchanged for longer than we can truly comprehend. Take a slow, deep breath, and as you exhale, try to match the rhythm of your own breath to that deep, cosmic pulse. There is no rush in the life of an aging red dwarf. It has all the time in the universe. It does not need to burn brightly to be significant. Its power lies in its endurance. It is a guardian of the darkness, providing just enough light to see by, just enough warmth to sustain, without ever demanding attention. In this stage of its life, the star is a symbol of absolute reliability. If you were to return to that twilight world 1 billion years from now, the sun would be in the exact same spot on the horizon, glowing with the exact same soft amber intensity. This stability is a rare gift in a universe that is often defined by change. We live in a time of great celestial activity, where stars are being born and dying in spectacular displays. But we are also moving toward a different era. Because red dwarfs are so efficient and so calm, they are the ones who will witness the changing face of the cosmos. They are the marathon runners of the galaxy, pacing themselves while others sprint toward their end. As the great clouds of gas begin to thin and the more volatile stars begin to exit the stage, the red dwarf remains, its quiet light a constant presence in the deepening shadows of the far future. We are moving now toward a vision of the universe where these small, steady stars are the primary keepers of the light, transitioning from the busy, crowded galaxy we know today into a much older, much quieter neighborhood. As we move forward in time, millions and then billions of years into the future, the character of our galaxy begins to shift. We are currently living in a golden age of star formation, a time when the great molecular clouds we spoke of earlier are still rich with hydrogen, still heavy with the potential for new life. But these nurseries are not infinite. Each time a new star is born, it claims a portion of that gas, locking it away within its core. While some of that material is returned to space when stars die, much of it remains trapped in the remnants, the quiet, cooling husks of stars that have finished their journeys. Slowly, over spans of time that defy human imagination, the great clouds of the Milky Way will begin to thin. The vibrant blue-white stars that currently define the spiral arms of our galaxy, the ones that burn hot and fast, will be the first to go. Without new gas to replace them, they will fade one by one, like the bright lights of a city being extinguished at the end of a long night. But as the galaxy grows darker and quieter, the red dwarfs will remain. They are the ultimate survivors, the stewards of the long twilight. In this distant future, the Milky Way will no longer be a brilliant tapestry of varied colors. Instead, it will glow with a soft, uniform amber light. These small stars are the last lanterns of the galaxy, and they will keep the lights on for trillions of years after the more famous stars have disappeared. Think of the comfort in that endurance. Even when the universe is 1,000 times older than it is today, there will still be light. There will still be warmth. These stars are so efficient that they can stretch their modest fuel reserves across eons, providing a stable, unchanging environment for whatever worlds might orbit them. They represent a deep cosmic patience. In this era of the red Milky Way, the universe will feel much more intimate. The distances between stars will still be vast, but the stars themselves will be consistent, reliable, and incredibly long-lived. They are the guardians of the far future, ensuring that the story of the cosmos doesn't end quickly, but lingers in a peaceful, steady glow. It is a time of great stillness, where the frantic energy of youth has given way to a wise and enduring maturity. But even a journey that lasts trillions of years must eventually reach a new stage. As we sit in the soft light of these last lanterns, we have to wonder what happens when that final, carefully managed supply of hydrogen begins to run low. Even the most patient star, having spent a trillion years burning its fuel with expert precision, will eventually face a change in its internal chemistry. As the very last of the hydrogen is drawn into the core, the red dwarf prepares for a transformation unlike anything else in the universe, a transition into a state that no human eye has ever seen, because the universe simply hasn't been around long enough for it to happen yet. As the red dwarf enters its twilight years, not in billions of years, but in trillions, it begins a transformation that is as beautiful as it is rare. In our current era of the cosmos, we see stars of all kinds, giants, supergiants, and middle-aged stars like our sun. But we have never seen the final stage of a red dwarf. The universe is simply too young. At nearly 14 billion years old, the universe is still in its infancy compared to the lifespan of these patient stars. We are living in the very morning of the universe, and the end of a red dwarf's life is a story that won't be told for a very, very long time. When a red dwarf finally begins to exhaust its hydrogen, something counterintuitive happens. Instead of simply fading away like a dying ember, it begins to glow more intensely. Because these stars are fully convective, meaning they have been stirring their fuel constantly from the surface to the core for trillions of years, they remain remarkably well mixed. As the hydrogen levels drop and the helium levels rise, the star's interior becomes more transparent to the energy trying to escape from its core. This allows the heat to radiate out more efficiently than ever before. As the temperature on the surface rises, the color of the star begins to shift. The soft, familiar orange-red glow that has defined the star for an eternity starts to brighten and transform. It moves slowly through the spectrum, turning yellow, then white, and eventually it reaches a brilliant, piercing blue. Astronomers call this hypothetical stage a blue dwarf. It is a phase of life that is predicted by our most advanced computer models, a mathematical certainty that remains hidden by the vastness of time. Imagine a universe trillions of years from now. Most of the gas clouds we spoke of earlier are gone, and the great spiral galaxies have settled into quiet, elliptical shapes. In this deep, dark future, these blue dwarfs would appear like rare, shimmering sapphires set against the velvet black of space. They are the final energetic pulse of a life lived with incredible discipline. It is a moment of unexpected radiance, a final surge of warmth before the long, slow cooling begins. This blue phase is relatively brief, at least by the standards of a star that lives for trillions of years. It might last only a few billion years, a mere blink in the eyes of a red dwarf. During this time, the star is hotter and more luminous than it ever was during its long youth. It is a final, beautiful flare of light before the end. It is as if the star is gathering all its remaining strength for one last, brilliant display of its presence in the dark. But because no red dwarf has ever reached this point, the blue dwarf remains a secret of the future. It is a chapter of the cosmic story that hasn't been written yet. We know it will happen because the laws of physics guide the stars along this path, but for now, it exists only in the quiet calculations of scientists and in the silence of our own imaginations. There is a peace in knowing that the universe still has so much ahead of it, that we are part of a story that is only just beginning. Take a slow, deep breath and let the scale of that time settle over you. The fact that the universe is still so young that its most common stars haven't even finished their first chapter is a comforting thought. It makes our own lives and our own time feel like a precious early spark in a very long night. We are the early witnesses to a story that will continue long after the Earth and the Sun have passed away. As the blue dwarf eventually spends the very last of its nuclear fuel, the intense heat begins to subside. The brilliant blue light softens, and the outward pressure that has held the star up against the pull of gravity for so long finally begins to weaken. The star has no more fuel to burn, no more energy to create. It begins a final, graceful contraction, shrinking down and settling into its ultimate resting state. This transition marks the end of the star's life as a source of nuclear fire, moving it toward a state of eternal, quiet cooling, where it will spend the rest of time as a silent, dense relic of the light it once was. As the final embers of nuclear fusion flicker out, the star undergoes its last great transformation. It does not go out with a violent explosion or a dramatic collapse into a shadow. Instead, it settles into a state of quiet, dignified rest. The star shrinks one last time, condensing its remaining matter into a sphere roughly the size of the Earth. This is the birth of a white dwarf, specifically for the small stars we have been following, a helium white dwarf. Because these stars were so efficient, mixing their fuel so thoroughly, they leave behind a pure, dense core of helium, a celestial relic of a life lived for trillions of years. Imagine, if you can, the sheer density of this new form. Though it is no larger than a planet, it still holds a significant portion of the mass of a star. A single teaspoon of this material would weigh as much as a heavy truck here on Earth. Yet, despite this incredible pressure, the white dwarf is not a place of chaos. It is a place of profound stillness. It no longer generates its own light through the frantic clashing of atoms. Instead, it glows with a gentle, borrowed radiance, the stored thermal energy of its long, long life. It is like a stone that has sat in the sun all day and continues to hum with warmth long after the sun has set. Visually, this white dwarf is like a diamond-like ember suspended in the infinite dark. In the beginning of this phase, it shines with a brilliant, pure white light, but it has no way to replenish that heat. Very, very slowly, over timescales so vast they dwarf the current age of the universe, the ember begins to cool. The white light softens into a creamy yellow, then a deep, warm orange, and finally a faint, ghostly red. It is a slow cosmic cooling, a gradual fading of a light that once stood against the darkness for eons. Eventually, in the unimaginably distant future, the white dwarf will cool so much that it stops emitting visible light altogether, becoming what astronomers call a black dwarf. But this process takes so long that not a single black dwarf yet exists in our universe. The universe is simply too young for any star to have finished this journey. Every red dwarf that has ever been born is still out there, still shining, still in the very beginning of its story. Let that thought bring you back from the far reaches of the future. Let the vast, cold time scales of the white dwarfs fade away and bring your awareness back to the present moment, back to the safety of your room, the softness of your blankets, and the steady, quiet rhythm of your own breathing. We have traveled trillions of years into the future to see the end of a star's journey, but now we return to the here and now, where the stars are still young and the night is still full of light. The great cycle of the cosmos is not just a story of endings, but one of constant, slow-motion presence. While we look at the distant fate of these stars, we must remember that the universe we inhabit right now is vibrant and alive, with the very same atoms that will one day form those cooling embers. The journey from a cloud of gas to a steady red dwarf, and eventually to a quiet white dwarf, is a testament to the endurance of matter and energy. It is a reminder that nothing is ever truly lost. It only changes form, settling into new rhythms and new states of being. As you lie there, feel the weight of your body pressing gently into the mattress. Much like the steady, patient pull of gravity we have discussed, there is a profound peace in the realization that we are part of this timeline, a brief, beautiful moment in the early chapters of a much larger story. The atoms that make up your pillows, the air you breathe, and the very heart that beats in your chest were all shaped by these same cosmic processes. You are a part of the stars, and the stars are a part of you. Take a slow, deep breath in, feeling the coolness of the air, and exhale softly, letting go of the vastness of the future. The universe is wide, and its timeline is long. But in this moment, all that matters is the stillness of this room and the comfort of your rest. We are moving back from the cold, dense embers of the future to the warm, familiar cradle of the present, where the story of the stars continues to unfold in the quiet glow of the night sky. The universe is the ultimate recycler, a master of patience and transformation. While we have looked at the long, slow cooling of red dwarfs into white dwarfs, it is important to remember that the matter within them and the matter scattered throughout the cosmos is part of a grand repeating cycle. The vast clouds of gas and dust we spoke of earlier, those quiet nebulae where stars are born, are not just made of primordial gas from the beginning of time. They are enriched by the legacy of stars that have come before. When massive stars reach the end of their lives, they do not simply fade, they scatter their heavy elements back into the interstellar medium, seeding the clouds with the ingredients for new worlds. Every atom in the cosmos, beyond the very simplest hydrogen and helium, was forged in the intense, pressurized heart of a star. The universe began with very little variety, but through the life and death of countless suns, it has grown rich and complex. This is the concept of reticled stardust, the idea that the materials making up our galaxy have been through the hearts of stars multiple times, being refined and transformed with each generation. The carbon that forms the basis of your cells, the oxygen you are breathing in right now, the iron in your blood and the calcium in your bones were all built, piece by piece, atom by atom, inside the nuclear furnaces of ancient stars. As you lie there in the quiet of your room, try to feel the weight of that connection. It is a physical reality that binds you to the furthest reaches of space and the deepest parts of time. The very same gravity that gently pulled those clouds together to form a steady, glowing red dwarf is the force that keeps you grounded and safe in your bed tonight. The atoms in your left hand may have originated in a different star than the atoms in your right hand, drifting across the light years for eons before coming together to form you. You are a small, quiet part of the universe that has gained the ability to wonder about itself. Take a slow, gentle breath. As you inhale, imagine the oxygen molecules entering your lungs as tiny messengers from a distant past, forged in a world of heat and light so that you might breathe in the cool, still air of the present. As you exhale, feel your body settling even deeper into the softness of your blankets, shedding the tension of the day, just as a star gracefully sheds its outer layers. There is a profound sense of belonging in this realization. You are not a stranger in the cosmos. You are made of the same substance as the stars you see through your window. There is no need to hold on to the complexities of the day or the vastness of the facts we have explored. Like the dust that settles in the light of a fading sun, let your thoughts settle now. The atoms that make up your bed and the air around you are billions of years old, yet they provide a stable, familiar cradle for your rest. Everything is part of the same enduring story, a story of light, of gravity, and of a quiet, persistent existence. You are part of a grand, ancient rhythm that has been unfolding since the dawn of time, and right now, that rhythm is slowing down, guiding you toward the peace of the night. You are safe, you are connected, and you are ready to let the stars watch over your sleep. We have traced the long, slow arc of a star's life, beginning in the silent, cold depths of a nebula and ending in the eternal, steady glow of a red dwarf. We have seen how the universe builds something vast and beautiful from the simplest of ingredients, hydrogen, gravity, and time. From the first stirrings of a molecular cloud to the final diamond-like cooling of a white dwarf, the story of the cosmos is one of persistence and quiet transformation. It is a journey that spans trillions of years, yet it is all contained within the same laws that govern the world around you tonight. But now, the journey of learning is complete. The facts and the figures, the trillions of years and the billions of miles can all begin to drift away. They are like distant stars on a cloudy night, still there, but softened and blurred by a gentle, comforting haze. There is nothing left for you to remember, and nothing left for you to hold on to. The universe is vast, yes, but it is also a place of profound stillness. That stillness is here with you now in the weight of your limbs and the slow rhythmic beat of your heart. Take one more slow, deep breath, feeling the air fill your lungs before releasing it fully. With that breath, Let go of the need to understand or to visualize. Let the concepts of light years and nuclear fusion dissolve into the simple physical sensation of your blankets against your skin. Feel the warmth of your bed as if it were the soft orange glow of a distant sun, cradling you in the dark. The journey through the cosmos has brought us back to this very moment, to the quiet safety of your room. The stars are in their places, burning with a steady ancient light, and you're exactly where you need to be. There is a deep cosmic permission to rest. The same laws of physics that govern the galaxies are currently ensuring the steady rhythm of your breath and the restorative peace of your sleep. You are supported by the earth beneath you and the atmosphere around you, a tiny, precious part of a grand and beautiful whole. As you drift further into the softness of the night, know that you are a part of everything we have spoken of. You are the stardust, the gravity, and the light. You are the universe experiencing itself in a moment of quiet reflection. There is no more work to be done today. The stars will continue their long, slow dance without you, and you can trust in the stability of the cosmos to keep everything in its place while you sleep. Sleep now, and let your dreams carry you across the silent nebulae and past the glowing red suns. May your rest be as deep as the void and as steady as the stars. You are safe, you are home, and you are part of the light. Good night and peaceful dreams.